Ah, yes, sorting, every computer scientist's best friend. Welcome to CS302 assignment 1. And this assignment, as you can already see, we're going to be implementing this cocktail shaker sort using a linked list. So this cocktail shaker sort algorithm is really just a bit of a modified version of bubble sort, but it's going to really bubble elements from left to right and right to left. It's a more of I guess a faster version of bubble sort, but not really faster asymptotically, but faster than these typical bubble sort algorithm. So I'm going to cover the actual algorithm towards the end of this video, but I'm going to first start off with just talking about this linked list data structure you're going to have to implement for this assignment. So this is basically, in a sense, a warm-up from CS202. And I apologize if I'm using a dark theme PDF. I do provide a light and dark theme assignments or write-ups for all my assignments, depending on what's your preference. But I think dark theme is a little nicer on, I guess it's not going to burn my eyes too much as I'm going over this assignment. So anyway, let's go ahead and talk about this class. So we're going to have a class called LL, it's short for linked list, and it's going to be a templated type. Whereas remember, a linked list, as you remember from CS202, you can really store a list of any type. You can use integers, doubles, characters, strings, and also any custom type as well. So really, there's no reason why we shouldn't have this data type implemented where it could really store a list of any type you wish. So type name T at the very top, that's going to really be our data type. Now, in this assignment, we're going to be sorting a list of integers, so T is going to be an int, but of course, you want to just sort of write this class to be generic, where it could work really for any type, because a linked list for this sort of container, it's not going to do anything specific on our data. It's going to simply just maintain a list of data, but it's not going to really do anything specific on them, so really, it's a very nice structure to use with a template. So, as you may remember from CS202, this linked list is going to really just contain a set of nodes. Remember, the struct node is going to be the data type for each node in the linked list. And we have our T data. And then we have this node star prev, node star next. So it's going to be a doubly linked list or a two-directional linked list. So you can go left and right or right to left. So this node star prev is going to be a pointer that points to a left neighbor of a node in the linked list, and node star next will be a pointer that points to the right neighbor of a node. So that's that part should be relatively straightforward. Now the only issue here is this class Iterator, which is a class defined within class LL. Now in Java, this is actually you see this happening quite a bit. Now you may not have been exposed to this in CS202, but no fear, I will definitely talk about the syntax and how to understand this iterator class, which is defined within linked list. But let's go ahead and just talk about the actual members of our LL class first, and then I'm going to go ahead and discuss the iterator content later on. All right, so right here we have our our public and private members for our LL class. Let's first start with our private members first. So we have our node star head and node star tail. So since it's a doubly linked list, or in other words, you can go left to right or right to left, we want to have a pointer dedicated to point to that first node in the linked list, and one pointer that points to the end node in the linked list. So head is going to point to that leftmost, that front node of the linked list, and node star tail is going to point to that rightmost end node in your linked list. So that part relatively straightforward. Okay, so now going through our rest of our members here, we have our default constructor right there. So our default constructor is going to just simply set head and tail both to be null. We're going to simply declare and initialize an empty linked list. So if head and tail are both equal to null or null PTR, that implies we have an empty linked list. Okay, now we have our copy constructor below. Of course, you want to set head and tail also to be null over here. And then we have to do a deep copy of our linked lists. So we're going to be we're passing in a linked list object into this constructor, and we want to copy that into our linked list that's being created. So it's going to just do a deep copy of that linked list being passed into this constructor, and we're going to deep copy it into our, into our this linked list, into that linked list being created. So again, I'd imagine this would be relatively a review from CS202, so I'll just sort of leave the actual code parts out of this, but hopefully this is a review somewhat. Now we have our assignment operator next, which is going to really be very similar to our copy constructor. All we're going to do is simply just take this right-hand side, so whatever is in this parameter, that's going to be our right-hand side linked list. And we have a deep copy into our left-hand side / our this linked list. So remember, this is that keyword, remember? So essentially same idea, except in this assignment operator, we have to first deallocate the this linked list, and then we're going to deep copy this right-hand side linked list into that left-hand side * this linked list. Also, you want to check for a self-assignment. So remember, if let's say I have a linked list object called list, I say list equals list in main, well, then we don't want to do any work at all. So you have to make sure we check for a self-assignment. So I'm guessing that would be also a review from 202. Then at the very end, you return * this. And the purpose of doing that is if, let's say, you have list 1 equals list 2 equals list 3 equals list 4, then it can chain those assignments together. And then, of course, we have our destructor at the very end right here, which is going to simply deallocate the linked list. Now, just a disclaimer, you're not going to have to really use the copy constructor or the assignment operator in main, but on code grade, I'm going to have a separate sort of runtime test to make sure you did correctly implement your copy constructor and assignment operator. So I will check for that. It will not be worth a lot of points, but it will be worth some points. You have to make sure you write those correctly. Even though you may not use them in main, I'm going to still check for those. So just a disclaimer. Now, destructor is important because you want to make sure we have all memory deallocated so we don't have memory leaks in our program. So you have to do that as well. Remember, for destructor, it's simply going to just be like playing Pac-Man. You just do a head delete until each 1 by 1 has been deleted. So think of Pac-Man. 1 by 1 kind of eats up those. I don't know what those things are called in Pac-Man game, but those circles that he eats 1 by 1. It's like that, a destructor for a linked list. Alrighty, and now we have our head insert and tail insert, and then we have our swap nodes. So I'm going to go to one node and kind of, draw up how you would do head insert. And of course, that will help you write tail insert. And I'll give you an idea of how swap nodes works, but I'll probably go over the swap nodes content after I cover iterators. But let's first go to our one node board and just go over, I guess, some code for how to do a head insert into our linked list. Okay, let's go ahead and consider the following linked list right here. So we have each node, as you can see here, I have is sort of graph type, not graph paper, but graph screen. And we have each node is divided into 3 parts. The left sort of subblock is that previous. This will be the next, and this is going to be that data field. So we had the following linked list, just like this. So when we do a head insert, you want to insert something to the front of the linked list. So I'm not going to really give you the code for this, but I'll sort of draw out how you want to approach this. So the first thing you want to do is you want to create a temporary sort of pointer. So I can allocate a point, or not allocate, but declare a pointer, so node star temp. And remember, we have to allocate a node to this pointer. So we would say, remember, temp equals new node. So I guess I am kind of giving away some code here, but just in case you might have forgotten about how linked lists work. But remember, we allocate a node by saying temp equals new node, just like that. And of course, erase that right there. And of course, temp will point to this new node. So let's say I want to, so remember, for our function head insert, we pass in some parameter. That's going to be the value we're going to insert into that data field of this new node. So let's say I go ahead and do a head insert 7. Then of course, remember, you have to dereference this pointer temp and access that data field of that node that temp points to and assign 7 to it. So I'll leave that code, I'll leave that for you to work on that code, but remember, just you can use that arrow operator to dereference this pointer and access the correct field. Now, this node would be your front node from now on. So you want to make sure that the previous is set to null, because the head node has no left neighbor. So you want to make sure we have this. Now, we have to make sure that this node doesn't in fact point to that front of the linked list. So, we have this head pointer which contains the address of that node that contains 5. I want to make sure that temp, that node that contains 7, its next has to point to the node that head points to. So the idea here is, we just have to do this. So, I guess just as a hint, not a hint, but the solution, remember, just temp arrow next equals head. That's going to set that node to point to the node that contains 5. And of course, you have to set this pointer to point back. So you have to, simply have head arrow previous equals temp to have this node's previous contain the address of that node that temp points to. And then of course, you have to set head to point to that new front node. So remember, just say head equals temp. And what that will do is it's going to just set this head pointer to point to that node. At that point, we're done. So all we have to do literally is allocate a new node and set that node's next to point to that head node, set the head previous to point back to that node we just created, and then move the head pointer over by just simply doing head equals temp, and then we're done. Now, one sort of issue that happens is a lot of times students typically try to say delete temp, because I want to delete the address that temp contains. You don't want to say delete temp, and in fact in C++ the keyword delete is a very misleading word. Remember, if I say delete temp, it's going to actually deallocate this node right there, which means now head is a dangling pointer and 5 points back to a dangling pointer. So you have a busted linked list basically. It's like having a centipede with a broken leg. You have that at this point. So you do not want to say delete temp. Now, temp is locally defined in the function head insert. So really all you have to do is just do nothing at all and temp will disappear. But if you want to be very strict about this, you could say temp equals null, or you can say, of course, temp equals null ptr. You could do that, which will wipe out the address, so temp will contain no address. That's okay, you can do that as well. But if you don't do anything at this point, once the function terminates, since temp was locally defined in that function, then that temp just goes away. So you don't have to really do anything at this point. So do not say delete temp is the real key to this. So of course the code is really a few lines of code, just allocate the node and sort of modify some next and previous pointers. Now, one thing you want to also worry about or consider is, what if you have a case where, let's say, you have a situation where head and tail both point to null or null ptr. Let's say we have this situation. So let's have an alternative scenario. So we have this, which when you're first going to insert into empty linked list, this in fact will be your situation. So when you have this and you call head insert, let's say I call head insert 5. I want to insert 5 into this linked list. What will happen here is, of course, you check to see if head and tail are both null. If they are, then you're going to essentially assign a node, allocate a node. So maybe you would say head equals new node, right? Which will set head equal to this node. And of course, tail will still point to null. So what happens is, just to remind ourselves, we say head equals new node, and then tail just remains like this. And you first check to make sure if head and tail both equal null, you have an empty linked list. You have this scenario. Now the example above, if head and tail not equal to null, then you have at least one node in your linked list. So then that will, this scenario I went over right here covers the general case. We have is one edge case we have to consider right there. So of course, we say head arrow data, we'll assign 5, and this is going to be a node. This node is going to be the front and back at the same time. So you want to make sure you set tail, so say tail equals head, which will essentially set tail and head to equal to this node. And of course, we'll just set this node's previous and next. So head arrow previous and head arrow operator next equal to null, because this node in fact will be the head and tail null. So make sure that if you do have an empty linked list and you do a head insert, you just simply assign head equal to new node and make sure head and tail both point to this node, because this node is simultaneously the front and back of your linked list. Now, you have to go over how to write the tail insert function on your own, but really a tail insert is very similar to head insert, except just in reverse, I suppose. So that was our head insert code. So now let's go ahead and cover the rest of the content in this linked list class. Okay, so now we can talk about this iterator class, which is defined inside of our linked list class. So an iterator is really just pretty much a pointer, except that it sort of hides all the private members, or the current pointer is hidden inside of it. So this is mostly going to be used in main to allow us to give us that flexibility to traverse the linked list like a pointer, but without exposing pointer data. So we have this friend class LL defined above. The whole idea of this is if we were to declare an iterator object within our linked list class member functions, we would be able to actually access those private fields. However, there's no real need to use an iterator inside of your class linked list, except for really just the begin and end functions only. So I guess that's probably the only spot we're going to really use iterators at all. But let's go ahead and go over these members, and I'll go ahead and I'll talk about how you can think about them in your program. So basically, we have this constructor, which sets the current to null. The second constructor is going to assign whatever pointer I pass into this constructor, it will assign it to current. That's all we have to do. Then we have this postfix plus plus and minus minus. Now, this is not going to really behave like a real true postfix operator, because I don't know, I guess I'm not really I'm not a big fan of these plus plus minus minus operators at all in C++, but I think it's not going to really be a true postfix. But the whole point of having this int as a parameter is just so that this plus plus operator goes after the iterator when called in main. If I didn't have an int right there, then this would be a prefix operator, so plus plus would go in front. I know the plus plus going in front or after the variable name does have an actual difference, but we'll just assume that the plus plus will be really it's going to update the pointers, the current pointer first, and then return the updated version of it. But we'll get into that in a second. And then we have our equals equals not equal to compare between two iterators to make sure if they're pointing to the same node. Okay, so let's go ahead now and talk about how to actually use these in our program, in our main, just so we get an idea of really how these plus plus and minus minus really work when we write our main program. Okay, let's suppose we have the following linked list. So this is my code in main I would use. So this is how we declare an LL object in main. We create our user LL type, and then the template will be int. So that means that that T sort of placeholder in our class is going to become int and then list. And let's suppose I did the following. I call tail insert 4 times. So I first tail insert 7, then tail insert 5, then 1, and then 2. So I have the following linked list. Okay. So the next thing is I didn't really cover the begin and end functions, but it's in the write-up and I can talk about it right here. So all the begin does is it returns an iterator object whose current equals head. And then the end function, at least from our program, end is going to be a function that returns an iterator whose current equals tail. So really, it's a single line of code, to be honest. That's all you want to do is just simply allocate allocate an iterator object inside of our begin function, assign its current equal to head, and return this iterator. So pretty simple. Now, let's say I want to go ahead and I want to iterate through this list in my program. So I'm going to actually move this down a little bit so I have some space here to draw the linked list, draw the iterator content. So I'll put this down over there. Then I'll zoom out so you can see everything. Okay, so I'm going to go ahead and sort of two-column this code, or maybe multi-column this code right now. So if you want to declare an iterator in your program in main, you would have the following. You would say ll int, then apply this scope resolution operator, iterator it. Now, we use this scope resolution operator because iterator is a class defined within our linked list class, or LL class. We have to use that. So telling us that, okay, well, I want to create an iterator object, but it's actually defined within the linked list class. That's why we have to use that operator right there. So right now, it, we use the default constructor to set it. So it's current points to null. So let me draw the it object right here. So here's it. Let's assign, let's say, a box to this. So we have this object. Now we have current defined as a private member defined within this it iterator object. Now, if I go ahead and say it equals list dot begin, well, list.begin is going to return an iterator whose current equals head. And right now, it's going to apply the assignment operator on this iterator. So it's current is also going to equal head at the end of the day. So what happens is this. Simply because since these two are both iterator objects, it's going to just simply use this assignment operator to just simply copy the right-hand side iterator into left-hand side. So now we have this situation. So in the iterator class, we have this star operator also defined, which if you look at the PDF, what the star operator does is simply retrieves the actual data of the node that current points to. So if I were to do something like this, if I say standard cout star it, and then escape sequence for a new line, what this does is the star it is going to return 7, because 7 is that data field of that node that the iterator points to. So for a star operator star function for iterator class, the only code you have to write would be return current arrow data, because you want to return that data field of that node that the iterator points to. And that current field within the iterator object is the pointer that points to a node in the linked list. So it would just simply be return current arrow data. Easy as that. And then if I go ahead and do something like this, it plus plus, the plus plus is supposed to move the iterator over to the right, one node over. So the result will be just simply this. So this operator plus plus function, all it's going to do is say current equals current arrow next. That's that general way, that's that universal way to move a pointer over to the next node in the linked list. So that's all out. And then of course it returns star this at the very end. And then that will cause iterator to move over to the next node. Then of course if I just want to access something, I can just say standard cout and then star it is we're gonna overload that dereference operator for iterators. It's going to just basically return 5 because 5 is the node that it points to. And also I could, also do something like it minus minus, which is going to simply move the current over to the left by one node, put it back to the front like this. So really, the star operator will allow us to access the actual data field of that node that the iterator points to, and then plus plus the minus minus will allow us to move left and right. So all you have to do is set it equal to list.begin or set it to list.end, and then you can just sort of navigate through the linked list by doing plus plus and minus minus. So you have to just simply overload these operators. So operator star returns that data field of that node, and then plus plus and minus minus just simply move it over. So you just set current equal to current next, and then for minus minus it would be current equals current arrow previous or prev, and then return star this at the very end. And of course, for equals equals not equal, all you have to do is just simply if this arrow current equals, so I think I have the actual function right here. So right here, we have RHS object. So just simply to say this arrow current equals to RHS dot current. If they're the same address, return true, else return false, and of course, if not equal, the same concept. So at least I hope that this example kind of gave you an idea of how iterators are used. It just in main allows us to sort of traverse sort of the linked list node by node, and it will allow us to access the data field within, because we can have to sort this linked list. You have to compare nodes to see which one's bigger or smaller, and then of course do swapping action. Now let's go ahead and now cover the last big function, which will be this swap nodes function. Okay, let's go ahead and consider this list again. So let's assume we have our list declared and we did a bunch of head and or tail inserts to end up giving us the following linked list you see in front of you. So the swap function, the way it's going to work is we want to swap two nodes in the linked list, but we don't want to simply just swap only the data value. We want to swap we want to grab the two nodes, lift them up and sort of move them geographically in this linked list. So let's say, for example, I have the following situation. I'm going to create two iterators right now. So I'm going to say llint iterator. I'll just have maybe I and j like this. And I say I equals to list dot begin. So of course I would point to this node right there. Let's suppose I say something like I++, which would move this iterator over by 1 to the right. So this iterator I, its current, will point to that node. Then let's go ahead and suppose I say j equals I, which will set j right there. And I'll just do something like j++ afterwards, which will move j over by 1 to the right. And we end up getting this scenario. So when we're doing our cocktail shaker sort, we're going to have to swap two adjacent nodes. So of course, it'd be very simple to simply just, take the data field. So it's 5 and it's 1, swap those values, and we can call it a day, which would be easy in this situation. But we want to be efficient with linked lists. And let's say, in a general speaking, what if each node's data field contained a big object, or it contained an array of some sort? Then just doing a simple, just copying the actual data points, or data values, sorry, would actually require a bit of an overhead. So if we just sort of take the two nodes and just sort of move these two nodes geographically, so the idea is, let me just sort of do this as best I can with one node. If I were to do the following like this, it's not grabbing the entire object. Let me just try this. There we go. If I just lift this up like that, and then lift it like this, this would be actually a lot more efficient, actually, to do this. Because the idea is that even if, let's say, we have a simple integer inside of each node, or we have a big data, a big object or an array, this is going to be a constant operation regardless of whether we have a small or big amount of data in each node. So taking those two nodes and literally moving them like how I did right there is the most efficient way. And of course, a linked list is very flexible like this. You want to take advantage of that right now. Let me go ahead and sort of Control Z and put everything back to the way it was. Okay, so that's going to be our end goal. We want to end up creating that. So how do we actually do this? So in our code, I'm going to sort of two column this right now. We would do something like this. List dot swap nodes I comma j. So this is going to run this function. So let's go back to the write-up for a quick second. So in the write-up we have these two iterators. Let me see, where is it? There it is. So IT1 and IT2. And they're both pass reference because we are going to actually update the addresses in these two iterators after we're done swapping. So let's go to look at the code. So we have IT1, IT2. So let me go ahead and just, for right now, just overwrite these I and j for a second and write them really as just it1 and it2. But in this function body, I and j really are just it1, it2 in disguise. So this part of the actual code in this function, it's going to be similar to, I guess, a SpongeBob where Mr. Krabs and Mrs. Puff were dating, and then there's one scene where Mr. Krabs was saying, we're not talking about this or talking about this, we're talking about, this. He starts drawing a bunch of lines all over the place. If you remember that episode. If not, then I guess sort of ignore what I just said right there. But anyway, this will involve a lot of pointer reassignments. So let's go ahead and begin. So the first thing you want to do is you possibly may want to create two temporary pointers, one that points to the left of it1. So I'll just call this maybe just I left. Another pointer, you want to call it maybe, actually maybe I should say I1 left, I'll call it, so it's a better name. And then maybe you can say I2 right. So you want to have these. So you of course can create pointers. You could even actually, for it1.current is going to be the actual address that points to this. You actually could create two additional pointers even. So you could do something like, you can create a pointer like node star I1 equals it1.current. And then same thing for I2, you can say I2 equals it2.current, just to sort of use only pointers, because no point using iterators in this function itself. So I'm going to go ahead and just sort of rename these once more. So I simply create two additional, I create actually 4 pointers. So node star I1, I2. So I1 would equal to it1.current, I2 would equal to it2.current. And of course, then I1 left, I2 right, just simply assign them accordingly. So I'll leave that to you right now. Okay, so here's where things get a little complicated. So basically, if I2 is going to, if I take this node and put it over here, then the idea is that this node has to point to that node, if that does make any sense, because this node is going to be the left neighbor of it2 from now on. So what you have to do is you have to make sure that you sort of reassign this node to point to it2. And then you have to set it2 to point back to that node. Because remember, if you're going to swap the 1 and the 5, then 1 is going to be to the left of 5 from now on. So that element that was to the left of 5 earlier now has to be left of 1. So this node is going to be the left neighbor of this node from now on. So you have to make sure that this node's next points to this node, and this node's previous points back to that. And then likewise, we have to make sure that if this node is going to be right here from now on, we have to make sure that we set this node's previous to point over here, and then this node's next to point over here. So the idea is that 5 will now be the left neighbor of 2. So we have to make sure that 5 points to 2 and 2 points back to 5. And of course, between 1 and 5, they're going to be swapped. So then you have to make sure we assign these pointers accordingly. So I1's next is going to point to 5, and 5's previous will point to 1. So this is a real complete, cluster sort of situation right here. So if I were to grab I1 left and I2 right, grab them, lift them up, then these wires will get all untangled, and end result is going to be sort of the following. Let me go ahead and just sort of stop the video and redraw this with the updated sort of look. So here we go, poof, there is the actual sort of redrawn version of this sort of linked list. So of course you can kind of go back and forth in the video to kind of just keep seeing, try to see how it all works out, but I just simply took this linked list right there and untangled the wires, and we end up getting this now. So now these two nodes have been officially geographically been swapped in this linked list. Now here's the other issue. So right now, after we're done with this, it1.current this points to that node as well, and it2.current points to that node as well, just like that. We have to swap these addresses because after we completed this swap, we still want it2 and it1 to still point to that same geographic location in the linked list as before. So before we began, it1 pointed to that node 5, it1 pointed to that second node in the linked list, and it2 pointed to that third node. We want to preserve that still. So you have to make sure that we just simply sort of swap these addresses, make sure it2 current points here, and it1 current points there, because that way it's still stable, as in they still point to that same position in the linked list before and after we swapped. So really, that's the entire, I guess that's the idea. So just sort of, I would suggest for this for this function, on a piece of paper or on an iPad or wherever, draw this out one by one. It's not very complicated, it's just very step by step, because linked lists have to first set this node's next, and that node's previous, and yada yada yada, all that stuff to make this whole thing happen. As you can see with this picture above, this insanity picture right there, do all that one by one, assigning things around to make sure things work. Now, there are a few edge cases to consider. So one is, what if it1.current was the head node? What if it2.current was a tail node? Then the idea is, remember, when we sort of swap these next and previouses, that pointer actually moved with that node. So remember from earlier, it1 current pointed here, but an it1 current actually then pointed over here. It sort of moved with that node. So you have to make sure we set them correctly. So for example, if it1.current is the head, let's say I want to swap, let's say earlier I wanted to swap 7 and 5, then these nodes would swap, but the head would move with 7. So the head is no longer going to point to that front node anymore. You have to make sure that after you're done, make sure the head still points to that head node, that new head node. Same thing for tail. So make sure you handle that case where if it1 current is head and it2.current is tail, make sure you handle that case, because then your tail node won't point to the tail anymore. It's going to point to maybe something to the left of the actual tail. So make sure you handle that. Also, the same idea, if let's say if it1.current equals a head, then I1 arrow left, which is this node, this pointer right here, would actually be null. So make sure you don't try to dereference that pointer, obviously, because then it would give you a seg fault. So make sure you handle that edge case. So I went over, I kind of drew this out for you right now and covered the very general case, but there is the edge case where it1 could be the head and it2 current could be the tail. And make sure after you're done with that you don't get a seg fault, because obviously to the right of I2 would be this pointer would be actually a null, and this would be a null potentially if you have that scenario. And make sure that the head is reassigned to the new head node. So if I were to swap 7 and 1, then 1 is my new head node, not 7. But unfortunately, head would move with 7. I have to reassign head like that. So I don't want to ramble too much further, but that's all there is to it. So of course, you have to use this swap nodes in your program, your main, to implement this cocktail shaker sort. So this concludes all of the linked list class content. Now I'm going to go ahead and give you an idea of how to implement this cocktail shaker sort in main. Okay, so for before we go into the main any further, we want to go over what our input and output will be for this program. So the input will be, you're going to read in a file name, open up a file stream, and then read a file. And the file will just really contain a set of integers, one integer per line, each line separated by end of line character. So you're going to have to do end of file control loop, and one by one just insert a number right from the file and insert it into your linked list object. Pretty simple. Of course, the output will be just output the list in sorted order and ascending order, so from smallest to largest. And don't worry about how you separate the output, because on code grade it's going to be set up where it ignores white space. So either a new line, a space, or a tab between each number, and the output is good enough. That's all you really have to do for the output. So code grade will ignore any white space, so use any white space you want to separate each number in the list to be output. Now, I actually gave you the sort of the Wikipedia link for cocktail shaker sort, and there it is. So I'm sorry about that bright light flash right there. So this graphic kind of shows what's going on essentially, but here's sort of the pseudocode for this. So you're really doing the following. So this for loop right there is really the inner for loop of bubble sort, and you have this outer do while loop right there. It keeps looping until this list hasn't been sorted. So you have to kind of figure out how to emulate this, but you know, you can probably take this pseudocode here and modify it to work with linked lists. So this portion of your loop is going to sort of bubble the biggest element and put it sort of in the back of the list. Then you have this second inner loop, which I guess looks like it takes the smallest element and tries to bubble it as far left as possible. So this loop takes the biggest element in the unsorted portion of your list and tries to bubble it as far to the right as possible. This one tries to sort of move the smallest as far left as possible. So really, in this list, what's going to happen is you're going to have sort of two frontiers in a way. So you have sort of the left half that's sorted and the right half that's sorted. And so if you're moving left and right, so if you're going from left to right, the biggest element is going to get placed to the front, that right frontier, if you will. Then when you go backwards from right to left, the smallest element gets kind of put into that left frontier, if that makes any sense. So that's sort of how this works. But of course, you can use this to help you kind of write the code for this. But you cannot use any counter control loop. So a for loop is going to be okay to use to iterate using iterators, but you can't use a counter control loop. So you have to have a few dedicated iterators that tells you how far you need to go when you're traversing from left to right or right to left. So I'll kind of give you an idea of how you want to think about that. So let's go ahead and go back to the OneNote board and draw out this cocktail shaker sort algorithm. Okay, so here is a very, I guess you can say a high-level view of the problem. So consider each of these numbers as a node, and then these arrows are kind of, remember, we have a two-dimensional or two-directional linked list. So you first start off by starting off the very beginning of your list. So I'm going to have, you know, my two iterators right here. So we'll have one iterator starting off here, and the other one will start off over here. So we have to go ahead and use our start operator, remember, on I and j to retrieve the numbers that they both point to. So start I would give us the value 3, and start j would give us the value 2. So of course, what would happen is you would go ahead and, in this case here, you want the biggest element to bubble to the very end, so 3 and 2 would have to swap in this situation according to that pseudocode. So I'm going to just go ahead and just, you know, obviously we would call swap nodes right here and pass an I and j. The end result is 2 would go over there and 3 would go over here. And of course, you don't just simply copy the data values, but you know, I'm just sort of doing a very simple view of this. And then I and j both have to move over by 1 like this. And again, we compare. So since 5 is bigger than 3, no swapping has to be done. So we just simply move over. Again, we check 5 and 8. So I and j in this case, so since j is the right side element, it is larger than the left side I. So we can, again, not swap, just simply move them over like this. Now here in this case, we see that, okay, I has a bigger value than j, so you have to swap them. So we go ahead and call swap nodes and pass an I and j, which the end result would be that 7 would go over here and 8 would go there. But of course, remember, just to recap, we're not just simply swapping data values, but you know, end result, at the end of the day, you'd get this result. Okay, then you go ahead and move the I and j over. You check, 9 is larger than 8, something has to be swapped over here. Then you move this over, compare 9 and 4. Since 9 is larger, we swap these. So 4 goes over here, 9 goes over there. Then we again move the I and j like this. Again, 9 is larger, so we swap them. And we hit the end of our list. So now what's going to happen is we're going to mark this node as sorted. So nothing will ever go beyond this point. So hint, hint, you may want to have some iterator pointing to this node, telling us that this is the end of that right frontier, or that right sorted portion. So now what happens in our next step, we're going to again do the same thing. We're going to have just I and j starting off over here. And do the same exact thing. Except now, if element to the right is less, we have to swap. So in this case, since 1 is less than 4, we have to swap these. So 1 would go over here, 4 goes over there, and we again move these over to the left. So this is kind of why having a doubly linked list is very convenient. We can simply just do I minus minus, j minus minus to move them over both to the left by 1. Same idea, we have to swap because I, when you start a j value contains 1, which is less than I value. So you put 1 over here, 8 over there. You move again. And again, this, I think it looks like we have to keep swapping because 1 is less than everything in our list. So 7 goes over here. 1 goes right there. We move them over once more. Again, same scenario. 1 goes here. 5 goes there. I think that's the right element, right value I just did. So anyway, then we have this. Again, we have to compare star I and star j, and because of the j element is less, you have to swap them. So end result would be just this. Then we have to go again. We swap the 1 and the 2. And now we're done. We hit the leftmost frontier. So now we're going to mark this as sorted. So I'm going to go ahead and maybe I'll just use green to denote this one. So nothing will go ever further left than this green element. Nothing will go further right than the red element. So we have the green and red. Those are going to be marking sort of, that's going to be the leftmost and rightmost frontier. So you may have to use some kind of iterator maybe to kind of determine that, okay, we don't go beyond this point. So let's do a few more steps here. So we're going to have now I will start off at this node and j starts over here. Now we're doing that other phase where we want to go ahead and put the biggest element to the right. So if the j iterator has a bigger value, then, or sorry, if the j is a smaller value, we have to swap. But here, since j is larger, we don't swap. So we just simply move the I and j over. Again, we move the I and j over. There's no swapping needed. Again, no swapping needed. Again, no swapping needed. But here we're going to have to swap because 8 is larger than 4. So we swap the 8 and the 4. And we move them both over, but now one of our iterators is going to point to that frontier. So now what's going to happen is you have to move this frontier over to this position, like this. Which means now that red box and everything to the right of red is sorted. So all of these elements right here are already sorted. But we want to sort of mark that we don't want to go beyond that point. So what happens, so when we have to go through this pass from left to right, once we hit that node that contains the 8, since we mark that node, we're never going to do anything once we hit that node. But let's just go ahead and do one more pass just to kind of see if we get the idea here. So we're going to have I setting over here, and j starts off over here. We check. The smaller one has to be swapped, so you have to swap the 7 and the 4. So the j, the rightmost position, if the rightmost between I and j, if j is less, sorry, then we have to swap them. So we put the 4 over there, and 7 over here. And again, we had to swap because 4 is less than 5. So 4 goes over there. 5 goes here. Move them over. In this case, nothing has to be done because the I iterator has a smaller value, so no need to do any swapping. Same idea here, I is less. And I hits that green frontier, so we're done. So now we're going to move that frontier over to the right by 1, which tells us that now everything to the left of that green, so the green box and to the left is sorted. So what happens is these elements are sorted and these elements are sorted. And of course, at some point, once the green and the red touch each other at some point, that means we have one big sorted list. So you want to go ahead and implement this sort of structure so you can kind of see that backwards, that left and right movement back and forth, which I guess emulates that cocktail shaker, I suppose is sort of why it's called that. I guess when you're shaking a cocktail, I guess making a martini, I guess you're supposed to shake it back and forth like that. I don't know. Like that's why it's called that, I suppose. I don't know. But anyway, so you want to implement this kind of structure, but once again, you don't want to use a counter control loop. So a for loop is going to be just fine. So with a for loop, often to iterate through a list, just to kind of give you an idea with a for loop, you can do the following. So you have to go ahead and in main create an iterator. I'll just call it, I have I and j like this. And you could have a loop that goes like this. So actually I'm going to do one more right here. I'm going to say ll int iterator. I'm going to create a special nil iterator. So I'm never going to ever reassign nil to anything else. So nil is going to always have its current point to null. So if you do something like this, where you say I equals list dot begin, and I is not equal to nil, I plus plus, this is going to iterate. And I guess I'll just, go ahead and just standard cout star I, that would iterate through your whole list like that. Now, of course, you could use a while or a for loop, and sometimes you want to make sure I hits null, but sometimes you want to have a different iterator being compared, because initially there's no frontiers set up, and once you create that one left to right pass finally happens, then the next time around you go from left to right, you want to have I maybe stop a little earlier, not to the very end of the list, but until it hits that red frontier, remember? So you have to sort of compare iterators either to nil in that first run, but then afterwards you're gonna have to set it, have it compared to something else. So it's gonna stop when it hits that iterator that points to that special node, telling us that we don't want to go beyond that point. So there's an example of a for loop that you can use, or a while loop. Just make sure it's not counter controlled. Don't actually count how many elements you have. Just use iterators to traverse, and when to stop looping once the iterator does hit a certain special iterator in the linked list. So let's go back to the PDF. So again, specifications, make sure you use the linked list object and iterator to traverse the linked list. No counter control loops. Of course, have your code nicely documented, and of course, make sure your code does not produce memory leaks. Now, again, just to remind you, we are going to actually we are going to sort of have a separate. We're going to test your code separately for the assignment operator and copy constructor. So even though it might not be used in your program, you still have to be able to make sure that you have those correct. So in this program, because of the fact that I have to test your code, you must create. So I'm going to go ahead and sort of write this over here in this PDF. You want to go ahead and you want to create an ll.h file. Here you're going to basically declare the class and implement the functions. Now with templates, it can be a little bit of a pain to get them to link to a separate header file with a CP file, but you want to have ll.h, where all you're going to do in that file is you're going to just copy and paste this class declaration, and of course you have to put all of these member functions implementations in just like this. So I gave you the function headings as they would appear in the linked list header file. So you first have your class declared at the very top, and you go ahead and implement each function afterwards. Then you want to go ahead and create a main.cpp, which is going to implement this sorting algorithm, cocktail shaker sort, like that. So you have to be careful. You must submit these two files, ll.h and main.cpp. Now, for the most part with my assignments, I'm going to have CodeGrid be very relaxed. It'll just compile whatever file you give it. But because I'm going to have a separate test case, a test just to make sure that your implementation of copy constructor and assignment operator are correct, I have to link a different main to your header file. So for that reason, I have to have this very specific naming convention. But for later assignments, though, I'll just be really loose. I'm gonna have it like on code grade. It'll just be G++ star.cpp. So it'll compile whatever you give it. But for this assignment, it's gonna be like that. So anyway, I hope this video sort of gave you a good idea, helped you out with this assignment. So I guess happy coding, stay safe, and until next time, take care, guys.